Welcome to Talk Tensors. Today we're diving deep into some really interesting research. It's tackling a pretty critical bottleneck in advanced AI systems.
All right, we're talking about these complex systems using LLM agents, large language model agents.
Exactly. They break down big problems, have specialized AI agents, handle pieces. It's powerful stuff.
Super powerful. But the problem is they often make mistakes. And figuring out why they messed up, that can be like searching in the dark.
Totally. The reasoning is opaque. They don't always fail in ways that make sense to us humans.
And it drags down the whole system's performance. Plus, manually checking everything is just impossible, really.
Which brings us to the paper we're looking at today, VARLA, a human-centered evaluation framework for interpretable verification of LLM agent failures. Big title, big idea.
It really is. It's trying to give us a clear lens, a systematic way to assess these failures, make them understandable, and cut down on all that manual checking.
Okay, so let's break it down, this VARLA framework. How does it actually work? What are the steps?
Well, it basically operates in three main stages. You've got planning, then agent execution, and finally, execution verification.
Planning first. So what happens there?
Okay, so you have a planning agent. Think of it like a project manager LLM. It takes the big, complex task, and it breaks it down into smaller, simpler subtasks.
Right, makes sense. How does it know what subtasks or who can do them?
That's where a really key piece comes in. The human-designed agent registry.
Okay, what's that?
It's like a directory. Humans define it up front. For every specialized agent the system might use, this registry clearly spells out its role.
Like what it's supposed to do.
Exactly. What it does, what kind of input it needs, what its output should look like. Say you have an ad agent, the registry says, takes two numbers, outputs their sum as a number.
So it sets clear expectations from the start. That seems crucial.
It is crucial. It directly tackles that problem of LLM outputs not matching human expectations. So the planner uses this registry
To create a plan.
Precisely. It generates a plan, often as a directed acyclic graph, a DAG.
Okay, a flowchart, basically.
Yeah, showing the sequence. Agent A's output goes to Agent B and C's outputs go to Agent D, and so on. It maps out all the dependencies.
And the planner also tells each agent what to do.
Yep. Generates specific instruction prompts for each agent in the plan, linking their little task back to the main goal.
Okay, stage one. Planning done. We have a DAG, agents have instructions. What's next?
Stage two, agent execution. Pretty straightforward. The specialized agents get to work.
They do their assigned subtasks.
Exactly. Using the plan, their prompts, and importantly, any outputs they need from agents that came before them in the DAG.
And this is, I imagine, where things can go wrong.
This is definitely a key point where failures can happen. Misinterpreting instructions, calculation errors, wrong output format. Lots of potential pitfalls.
And digging through all that manually is the nightmare VARLA wants to solve.
Exactly. Which leads us to stage three, execution verification. This is where the magic happens, sort of.
Okay, tell me about the magic. How do they automate the checking?
They introduce an agent verifier module. Think of it as an automated quality control inspector for each agent's output.
So it looks at what an agent produced and gives it a pass-fail.
Essentially, yeah. It's trained as a binary classifier, success or failure, based on whether the output meets those human expectations we talked about.
How does it learn human expectations? It can't read minds yet.
No, not yet. It's trained on human gold standards. Basically, humans look at a bunch of agent outputs, label them good or bad based on clear criteria, and the verifier learns from that labeled data.
Okay, so it learns from human examples. What features does it actually look at when it's making its judgment on a new output?
It considers a few things. First, those human-defined agent criteria we mentioned from the registry.
The rules for each agent type.
Right. For a subtract agent, is the math right? Is the format correct? Did it use the right context? And interestingly, they mentioned you could even use other LLMs as judges for these criteria sometimes.
Like an AI judging panel. Cool. What else?
Second, agent uncertainty. The verifier looks for signs of how confident the agent was.
How does it measure that?
Various ways. Maybe the agent literally says, I'm 80% confident, or you can look at technical things like the probabilities of the words it generated, entropy, things like that. They also check self-consistency.
Mean.
If you run the same agent on the same task multiple times, does it give the same answer? If it's all over the place, that's a red flag. Lower confidence or inconsistency often points to a higher risk of error.
Makes sense. If the agent itself seems unsure, maybe we should be too. Any other features?
Yeah, the third category is plan structure.
So where the agent is in that DAG flowchart.
Exactly. What kind of subtask was it doing? And also its position, how many agents feed into it, how many agents depend on its output, how far is it from the start or the end of the whole process.
Why does that matter?
It helps understand the agent's context and potential impact. A mistake early on or from an agent that feeds into many others might be more critical than a mistake near the very end. It's a more holistic view.
That is pretty comprehensive. Okay, so they built this verifier. Did they test it? How well did it work?
They did. They trained it using a random forest model that's a common machine learning technique and tested it on 4 different math reasoning datasets. Places like GSM-8K, Big Bench Hard, challenging stuff.
And the results?
Pretty good, actually. They reported an average accuracy of around 88% in correctly identifying whether an agent's execution failed or succeeded, according to the human label.
88% is quite solid. Was it consistent?
Generally, yes. High accuracy across different types of math subtasks. There were a few specific cases, like identifying operands in one dataset, where formatting issues made it a bit trickier, but overall quite stable.
Did they figure out which of those features were most important for the verifier? Like the uncertainty, the structure, the criteria?
They did ablation studies, yeah, where they remove features one by one to see the impact.
Yeah.
The human-defined agent criteria turned out to be the most important factor by a significant margin.
Wow. So really nailing down those expectations up front in the registry is key.
Absolutely. It heavily influences the verifier's success. It really reinforces that human-centered aspect.
Okay, so VARLA is good at spotting individual agent failures, but a complex task involves many agents. How does it tell you if the whole task is likely to fail?
Right, that's the next step. They use what they call verifier-driven aggregation metrics.
Aggregation, so combining the individual scores somehow.
Exactly, taking all those individual pass-fail judgments or maybe confidence scores from the verifier and rolling them up into one overall prediction for the entire task.
How do they do that? Just average the scores.
That's one way, the mean aggregator. They also tried simple things like a mine aggregator, just looking at the score of the single worst performing agent.
Assuming if one fails badly, the whole thing might fail?
Kind of, yeah. But they also explored more sophisticated structural metrics.
Ah, using the DAG structure again.
Precisely. Weighting agents based on their position, like how far are they from the start or end, or how many connections do they have, in degree, out degree. An agent whose output is used by lots of other agents, high out degree, might be weighted more heavily.
Because its failure would have a bigger ripple effect.
Exactly. The whole point of these aggregation metrics is to help users prioritize. If you have thousands of tasks running, which ones should you audit first? These metrics can flag the tasks most likely to have failed somewhere inside.
That sounds incredibly useful for managing these systems at scale. Did any particular aggregation method stand out?
They found that the simple mean aggregator and the out degree aggregator, focusing on agents that feed into many others, actually performed pretty well and consistently across the different data sets. So they could be good default choices.
Okay, and they showed this working in a case study. You mentioned math problems earlier.
Yeah, the mathematical reasoning case study was central. They defined their agent registry with agents for add, subtract, multiply, divide, identify operands, etc. Got human annotators to provide the ground truth failure labels on those tough math datasets.
And then showed VARLA could use the verifier and aggregation metrics to spot the agent errors and predict which overall math solutions were likely wrong.
Exactly. It demonstrated the whole pipeline effectively in a concrete domain.
So summing it up, VARLA seems like a really practical framework. It brings structure, it leans on human definitions of success, it automates the checking, and it gives you a way to predict overall task failure. A big step for making these agent systems more reliable and less mysterious.
Definitely. It's about making them more transparent, more trustworthy, and aligning them better with what we actually need them to do.
All right, let's shift gears to our novel notions segment. Thinking beyond this paper, where could these ideas lead? What are some exciting future directions building on VARLA?
Okay, one idea that seems really compelling builds directly on that human-designed agent registry and the feedback loop from VARLA.
Go on.
What if the registry wasn't static? What if it could adapt dynamically based on what the VARLA verifier finds?
So the system learns to improve its own agent definitions.
Kind of, yeah. Imagine the verifier consistently flags failures for, say, the divide agent when dealing with fractions. Or maybe when a specific sequence like identify operands then subtract happens.
Uh,
The system could then suggest changes, like, hey, maybe we should refine the divide agent's role description, or tweak its expected input-output specs, or even perhaps we need a new specialized agent just for fraction division.
wow, that's cool. Like automated system optimization.
Exactly. It's taking that human-agent collaboration a step further, using machine insights to refine the initial human design. It could make the whole compound AI system more robust, more adaptive over time, and maybe reduce how often humans need to manually tweak that registry.
I can see huge potential there, especially in really complex areas like, say, scientific research or planning,
Yeah.
where things are constantly evolving.
Definitely. More efficiency, better accuracy.
Okay, that's one really interesting direction. What's another?
Another avenue I find fascinating is integrating explainable AI, XAI, much more deeply into the agent verifier itself.
So moving beyond just pass-fail.
Right. Instead of just saying agent C failed, the verifier could provide a human understandable explanation for why it failed.
How would that work?
Well, it could potentially highlight which specific human-defined criteria were violated, or maybe point out suspicious patterns in the uncertainty metrics just before the failure, or even trace the error path back through the DAG. Agent C failed because it received faulty input from Agent A.
That would be incredibly powerful for debugging. Not just what broke, but why and how.
Precisely. It would massively boost the interpretable part of VARLA. Practitioners would get much richer, more actionable insights. You could use XAI techniques like S-shape or LIME to show which features the criteria, the uncertainty, the plan position were most influential in that specific failure prediction.
Faster debugging, faster iteration, more trustworthy systems in the end, especially for critical applications.
Absolutely. It leads to faster development cycles and hopefully more robust and reliable AI overall.
Both of those are really exciting extensions. It shows VARLA isn't just a solution, but potentially a foundation for a whole new way of managing these complex AI systems.
I think so. It provides a solid base to build upon as we try to make these powerful tools safer and more aligned with our goals.
So to wrap up our deep dive today, VARLA offers a really valuable human-centered way to interpret and verify failures in these increasingly common LLM agent systems.
Yeah, it's about making the process more efficient, aligning agent performance with human expectations, and ultimately reducing the cognitive load on the people building and using these systems.
It feels like a crucial step towards better accountability and building AI we can genuinely trust, especially when humans and AI collaborate.
Couldn't agree more.
For those of you listening who want to get into the weeds on the methodology and experiments, we'll put a link to the full research paper in our show notes.
Definitely worth a read if you're working in this space.
And that leaves us with a final thought to ponder. As these LLM agents get even more sophisticated, weaving themselves into ever more complex workflows, frameworks like VARLA are clearly vital. But how do we evolve these evaluation methods further? How can we anticipate and address entirely new, unforeseen failure modes in agent systems that might operate in truly open-ended environments? Something to think about.
A big question for the future.
Indeed. Join us next time on Talk Tensors as we continue exploring the cutting edge of machine learning research.